Hello, this is Dave Tabb. I am recording this video today to explain how we could create a sequence database from a bottom-up proteomics data set that includes just the proteins that have evidence from that bottom-up proteome in order to give us a relatively small number of proteins to search in top-down proteomics. So this is a case where our sample's been analyzed first by bottom-up proteomics and secondly in intact form to produce the proteoform data that we would need for identification. So for this, I'm going to be using the FragPipe software. You've probably heard of MSFragger. FragPipe is a user interface that sits atop it. So FragPipe is a Java program that in turn can launch several other programs, MSFragger being the search engine that it uses, Philosopher being a tool that encompasses many of the tools of the transproteomic pipelines, such as peptide-profit. Python has some modules that can also be called into play for handling very large sequence databases or spectral library generation. So in this case, this first screen, the config, is just going to show that we have everything installed. If this doesn't report that MSFragger is present or that Philosopher isn't present, you're going to have to get those things installed before the rest of those functions are available. It's not absolutely necessary that all of these be present. For example, I have not installed MS Proteomics tools, so I can't use the Spectrast tools in particular. All right, so the config in this case is good. All the pieces are in place. At this point, MSFragger has probably released yet another new version because they're very, very good about that. These tools are all under active development and new stuff shows up for it all the time. All right, next I'm going to click over to workflow. This is a pretty important concept because this determines what kind of search can be carried out. MSFragger can be used on stuff like data-independent acquisition or swath-type experiments. And in this case, we want to use it for a pretty standard, narrow standard database search. I have a few others in here that I've used. I'm just going to start with the default settings, and we will configure from there. If you have a fair bit of RAM on your computer, as I do in this case, 32 gigs of RAM, you will find that MSFragger is able to execute quite a lot more quickly. Likewise, it helps to have a lot of processor cores. So this is a relatively old server that's got a fair amount of RAM and a fair number of processor cores. This will certainly be a lot slower if you try to run it on a laptop with 8 gigs and 2 cores, for example. Not impossible, but certainly more cramped experience. We are going to start by loading the list of MS data files for analysis into this list. Normally when you have this opened on your screen, you're going to have a lot more dots to play with. For the purposes of this video, I've run at a relatively small resolution to make this all fit a little better in video. All right, so I'm going to go to the drive that contains my data set. Here is the E. coli set. I'm going to use bottom-up data for this particular experiment. And because I can, this is Microsoft Windows, therefore I can run directly against the raw files themselves. I don't have to convert them to MZML in advance. These are the 6 experiments that I've chosen as representing the shotgun bottom-up proteome of the sample, in this case of E. coli lysate. I'm going to select these raw files, and then I can pass down here and make sure everything got into place. All right, the files are all going to show up down there. I can now come over to the umpire tab. There's nothing I need to do with umpire because this is not a data-independent acquisition experiment, but I do have a little bit of work left on the database tab. Here you see that I've specified my FASTA file is located in this directory with that file name. This is the reference proteome from Uniprot for E. coli, but this contains 4,450 entries. It's exactly as it is when I downloaded it from Uniprot. It is the complete set of proteins known for E. coli K12. I have a little bit of work to make this ready for sequence database search. I'm going to add decoys, as you can see. And I note that the software gives the ability to add decoys and contaminants. Well, that's rather important because in this case I would like to be able to find evidence of proteins like trypsin and the keratins that may show up. And so I'm going to add those in. That's standard fare for bottom-up database search. Okay, so it's going to update the database by adding decoy versions of each entry and by adding the contaminants as well. This is a network process, so it has gone out to the network, done a little processing on this side, and now it's created a new sequence database that automatically replaces the one that I had initially given it. And as you can see, before I had 4,565 target sequences, now I have a total of 9,130. So each protein is now present in both forward and reverse orientation in my sequence database. All right, for the next stage, we need to configure MSFragger, and there are a lot of potential options for MSFragger. So I'm going to start by saying it's probably best for your first tries to stick with one of the standard configurations that exist here. We're going to start with what they call closed search. I tend to call it a narrow rather than a wide search, but that's just language stuff. So closed search means that we're going to compare to each tandem mass spectrum peptides that are very, very similar in precursor mass to what was observed as the precursor for that tandem mass spectrum. So closed search default config. There are a few things that I'm going to simplify to make the search run a little faster. I'm going to turn off mass calibration. It can be very useful for a search where you're really trying to maximize identifications, but in this case, that's not so important to me. I'm going to allow that the software may miss the monoisotope by 1 neutron, but not more than that, and that again is going to reduce the search space a little bit. We are, however, going to limit to only strict trypsin peptides, and we're going to require that the peptides be tryptic on both ends. So each end of the peptide is either an enzymatic cut site or it's the end of the protein, and that's it. Those are the only possibilities. Up to 2 missed cleavages, I do allow for clipping off the N-terminal methionine because that certainly happens a lot. The peptide length here is set from 7 to 50. That's not strictly speaking necessary in this case because what we're trying to do is just trying to get a catalog of what proteins are present. I don't think that searching for +5 peptides at really high lengths is necessary, so I'm going to cut this down to 40 in this case. I'm not going to split the database up. The peptide mass range I can leave as it is. This 40 will probably limit us to a lower number of a smaller size of protein overall. We have the ability to add some modifications. The ones that matter in this case are simply oxidation of methionine and the N-terminal acetylation of proteins. This square bracket in front of this implies that this can only happen at the, as you see, the protein N-terminal. So square bracket is a special symbol. And we also have this little hat symbol, the caret. So it's to represent that this is terminal on the protein in question. All right, so we have several different kinds of modifications we could add here. We might reasonably add something like deamidation, but I'm really not going to go into all the possible options there. I'm just going to stick with oxidation of methionine and N-terminal acetylation. It might be worth your while to note that in this case the software assumes that every cysteine has a fixed modification mass of 57 mass units. So cysteine will always be considered to be 160 Daltons, not 103. This is the assumption, of course, that you have used iodoacetamide, which is very, very common in the case of shotgun proteomics. If this isn't the case, if you use something like MMTS, or you used iodoacetic acid rather than iodoacetamide, then you would need to change that to either, say, 46 or to 58. It is also, of course, possible that you didn't use anything to modify cysteine, in which case you'd need to change that to a 0. But the assumption here is that you've used iodoacetamide, and that mass shift is fixed. All right. There are more advanced options that we can continue on to down here, but we're really not going to get into them because they don't come into play for this particular search, which, as I said, is designed to give us an inventory. On validation, we will need to do some validation. We need to turn those search scores from MSFragger into things like posterior error probabilities. So being able to determine what the probability of error is for each particular PSM is necessary. The defaults for closed search loaded when we loaded that template under MSFragger. So all of this we can leave just as it is. Yes, protein profit is playing the role for proteins that peptide profit does for PSMs, to be able to find the probability of correct identification for each protein. And of course, we want to generate reports. Now, I want to note that something that we haven't clicked on here is an option that says export FASTA subset. You might think that this is an option we have to select, but helpfully, that happens completely automatically, and we don't have to specify that it does happen. So that's a gimme. There's no quantification that we run in this case. We're not going to integrate chromatograms. We're not doing any sort of labeling with TMT or anything of that sort. And PTM Shepherd is not necessary because we're not running an open search. That's the typical way you might think of MSFragger, but it's perfectly capable of doing a good localization job as a standard normal database search engine. It is possible to do things like generate spectral libraries. I haven't installed the toolkit for doing that though. So we can proceed on to run, and I can clear this console. I can ask it where I want to write the outputs. I don't want to write it there because that's actually the wrong project altogether, but I can come back in here, select E. coli, and I'm going to create a directory just called MSFragger. Okay, so I can specify that MSFragger is where we want to write our output, and now I can finally do something like print commands to show all the commands it's going to run, but in this case, I'm feeling lucky. I'm simply going to click the run button, and off we go to the races. All right, so we see that a bunch of text flashed by. It does quite a few things up front here along the way. Oh goodness, and it just scooted itself right back over to the right side of the panel. That's fine. In any case, we see that MSFragger has started doing its business. The software is going to check that the sequence database is present and that it is readable. Of course, given that we just created it through the database tab, we know that that's in place. In checking spectral files, the software does not want to just assume that the list of files you've given it are all legible and do a bunch of work only to discover it's not actually useful. So in this case, it needs to check that each of those files is present and legible. And I want to note one other thing here, that the software is quite good at making use of all the RAM you've got on your machine. This computer has 32 gigs of RAM, and you see that the Java virtual machine is using 28 of them for doing this project. All right, so as it gets along, it's now screened through the raw files. This step that just flashed by of length 31, of length 32, of length 33 is enumerating how many different peptides from the sequence database were 32 of length, 33 of length, 34 of length. And you remember I had applied a maximum of 40 amino acids, which is why it has stopped there. We can see that in total, there are just under 1 million modified peptides that have been extrapolated from a protein sequence database of 9,000 proteins. So that's a cautionary note here, that there are lots of different modification variants and trypsin cleavage variants that result from a relatively small number of proteins. But one of the things I'm very grateful for is that the number of fragments that we need to compare to this can all be handled in one slice of RAM. The computer is going to load a whole bunch of this database index into RAM and process each file in one pass. If I had a very large sequence database, specified a large number of post-translational modifications, or specified a semi-triptych search, or did an open search, I might expect that the number of sequence candidates to be compared to the spectra was larger than it could hold in memory at one time. As a result, something like that might require multiple passes, and so I would see operating on slice 1 of 5 or 1 of 10. I think the largest I've run on here recently has been something like 28 slices. That's a job that ran overnight. But in this case, we don't have to wait that long. So the fragment slice is specifying all the different peptides that might be compared to a given spectrum. And for a given spectrum, we're able to look up very rapidly using its indexing which sequence candidates match to a fragment of this particular mass. So it's a really, really fast way to compare all of the spectra to all of the precursors that match it very closely in observed mass. And we see that here it has started with the first of the raw files that we were going to process for this. I believe there are 6 in total. So having figured out all of the different precursors that should be compared to the spectra, it can now start on the first of the raw files. It's probably worth noting that the machine is really, really busy, even though it seems on screen that not much is happening. But you can see that about half of the CPU power of this machine is being consumed, and a fair chunk of its memory is being used as well. As I mentioned, this is a relatively compact database search that we're doing, so having a having this all fit within 32 gigs of RAM is quite helpful. We see that the disk drive in the background is doing quite a lot, because a lot of this involves just slurping up the raw files, doing all the comparisons, putting that one away, and loading the next one. So in some ways this would be a whole lot faster if I'd actually run this from the SSD rather than the spinning hard drive. All right, so the first of the raw files, we see that there were 67,000 spectra collected. It's kind of amazing what new technology can do with these things. We're de-isotoping, which means that the fragments that appear in a given tandem mass spectrum are assumed to have different isotopic variants. That intensity is all getting shoved back into the monoisotope for each fragment. The matching process ran by very quickly, and the post-processing itself is pretty quick. I want to note that the database search is not what consumes all of the time, though. Remember that we're using Philosopher downstream to handle things like the peptide profit and protein profit operations. So the software excuse me, must be able to read the complete raw file, and these files are not small. It must load those all into data structures in RAM, do this pre-processing like the de-isotoping, do the comparison of tandem mass spectra to the proteoforms, to the peptides in this case, and then write that result. We can see it's already onto its second raw file. So for folks who are accustomed to thinking of relatively more traditionally designed search engines taking an hour on a given raw file, we are well and truly past those times. In this case, we're able to do our searches in minutes for collections of raw files. So I was somewhat hesitant to jump on the open search train when it first pulled out of the station, and when the first papers came out, I was rather skeptical of what was achievable with those. But what I'm not skeptical about is the ability to do my data analysis for traditional narrow database searching very, very quickly. And that's really a feature that I think most people have overlooked about these new open search engines. This is not true only of MSFragger. You could use something like pfind as well, another search engine designed around this concept of open search. Okay, so having finished the read of this file in 136 seconds, the de-isotoping took place in a little over a second. The search progress was the comparison of all these candidates to spectra took another 5 seconds. The post-processing took 5 seconds. So pretty much all of the time being consumed in this search is trying to read that raw file into a data structure in memory. That's a pretty stunning achievement, frankly, and it marks a real shift, I think, in how people will think about search. So we're already reading the third file and making good time. So you might think to yourself, well, I have access to a machine that has a lot of RAM, but it's not running Windows. And I'm pleased to say that there's no requirement that you run FragPipe or MSFragger in Windows. This is Java software. As a result, you can run it on a Mac or run it on a Linux machine as well. The question for me would be, does Philosopher also run in all those platforms? And I do know that Philosopher is available for Linux as well as for Windows. I think there may be a Mac build, but I'll have to ask Alexi about that one because I'm not actually sure. But at least the search part itself can be run on a Mac as well. Just because it's all Java software, it's content to do that. Of course, there is a limitation on that because the libraries for reading the raw files are intended to be run under Windows only. So it might be that you needed to start your search from MZML files instead on a different platform. All right. Let me see. I'm trying to think what else there is that I might want to say about it, but I'll leave space for your questions, of course, in the comments on YouTube, etc. I hope I can answer those because I don't always get notifications that those are appearing. But I will be glad to help where I can. I'm going to bring up the task manager again. You see that the memory in use has continued climbing a little bit, but we're still well under half of all the RAM that this machine has on offer. The task manager, by the way, is something that you can reach just by right-clicking on the Windows taskbar and selecting Task Manager. So as we go along, we see that there was this long period of disk reading, but when it finished this disk reading, it started doing some writing instead. But I want you to note that at the very same time that the disk stopped reading continuously, we had this huge spike in CPU usage. That spike in CPU usage reflects the fact that after the raw file is read, we can do the search itself. And that's what this great blast of processor time represents. Okay, I'm going to click back over to the FragPipe interface, and we should be able to see our current progress. We've already started raw file number 4. So having already finished half the search in just a few minutes' time, we're delighted that we can make this kind of rapid pace through this kind of analysis. You could ask yourself, is it expensive these days to buy a machine that can run this kind of operation? And I would note that the computer that this is running on at the moment is about 10 years old. So in this case, these are all used parts. The computer actually came with 32 gigs of RAM, so I didn't even have to upgrade that part. And in almost every case, even an old server hardware is usually able to outperform a laptop that you would buy. So it's not terrible to have something like this available to you. I would note, however, that so far I have not seen a lot of software tools out there for proteomics that make extensive use of RAM. So at present, I think of MSFragger as the one that is most aggressive in making use of RAM. There are cases where if I try to do a post-translational modification search that is more complex than, say, a phosphorylation search, that I frequently get an expansion in the number of candidate peptides to such an extent that it's no longer possible to run that in a single pass. Sometimes I even get a crash in this early stage of the software up here where it's trying to compute pre-compute the list of all peptides that are possible for the database. If I get a crash in there, I have a real problem because then I can't really split up the search into different slices. So for something like that, you really need to be able to have some of the extra tools installed that let you split up a sequence database across multiple jobs. Okay, so as we move forward, we see that we've now finished processing the 4th file. The 5th one will start slurping up shortly, and we'll soon be on our way to post-processing, which will take about the same amount of time, I think. I'm going to flip back to Task Manager to again show us the performance. This was all the disk reading is happening more or less continuously as it reads all of these spectra into data structures in memory. I would note that although the memory shown in use by this particular Java job doesn't increase, it's more or less set aside a huge fraction of the system RAM to be used just in case. In this case, we don't see a huge climb in the amount of memory in use right now because the memory already expanded to accommodate all of the spectra that we were reading on the first file, and the later files are not really going to add much to that overall memory demand. All right. So pretty soon this file should finish reading, and we should see a corresponding blast of CPU usage. Let's see if we can catch it from this side. Still reading. I can see that little line creeping across on disk D. Unless it's fooled me. It's possible. No, it's still reading file 5. That must be a large one. We see memory ticking upwards a little bit. I don't remember seeing this higher than 18.3 gigabytes so far, so it does seem odd that somehow the loading of these spectra into RAM should take a long time. But remember, it's not just it's not just creating a copy in RAM of every raw file on disk. It has to do an indexing of these spectra as well. And here, having finally finished the read, we see the big blast of CPU usage that represents the search itself. What I was saying is that in reading the spectra off of disk, the software is indexing all of the different fragment ions that are seen for a given spectrum. So if you have a particular peptide sequence, you can ask which spectra across this raw file contain a fragment that matches this particular fragment from this sequence. It's kind of this two-way associative index. So it's what's making the search time go so quickly, but it does require a little more thinking on the raw file read. Okay, file 5 is done, 6 is in progress. Once this one finishes, we're off to the races with Philosopher showing its stuff. If I'm doing my math correctly, 150 seconds is 2.5 minutes. So 2.5 minutes to read the raw file into this this fragment index, to rapidly do deisotoping, of course, on route. And then only 3 seconds for matching time. The world has shifted. Just for reference, the original Sequest algorithm was largely developed on a Pentium Pro 200, which is to say 200 megahertz. Given that this 10-year-old server is 2.8 gigahertz rather than 200 megahertz, it's astonishing how quickly we've seen sort of a parallel race taking place. The number of spectra you could generate in a 2-hour experiment on an LCQ ion trap back in the late 1990s was something like 2,000 tandem mass spectra over the space of 2 hours. Today, you can probably on some instruments, the non-Orbi Velos, you could probably easily generate more than 100,000 tandem mass spectra in that much time. All right. If we pull this to the side, we see that peptide profit is beginning its initialization. Peptide profit, of course, is going to work with these tandem mass spectra to produce posterior error probabilities for individual PSMs. So to complete my point, I was going to say that Intel is famous for Moore's law, which is that every 18 months, I think the original was, we expect to double the amount of processing power we have available in a typical computer. This produces, of course, an exponential effect, that we have a doubling of processing capability every 18 months. The mass spectrometry world has a very comparable phenomenon, though. The number of tandem mass spectra that we can create in a given amount of time is also doubling at a very fast rate, even now. So it is, but for all that we have all of these next generation proteomic technologies being considered that don't use mass spectrometry at all, it's kind of stunning to think that mass spectrometry has become so very nearly comprehensive in its ability to identify proteins from very mind-bogglingly complex samples, unimaginably complex samples from the old LCQ days. So we've had this sort of tilt back and forth. Are computers growing in processing power more quickly or less quickly than mass spectrometers? Or is the search time required for a given generation of instrument much, much worse than in the past? I remember that when the LTQ first came out, people were like, how can we make the processing faster? Because this is too slow. But of course, as computers got better, we don't really think of LTQs as a problematic instrument to keep up with on our modern PCs. All right. So we've now started Peptide Prophet, which is doing its analysis of the targets and decoy PSMs for each of these PEP XML files that have been generated. It's going to iterate through the statistical models for fitting distributions of presumably false identifications and presumably true identifications. This process of expectation maximization requires it to try lots of different random positionings of these distributions to find the best way to fit them to it. But I would note that even from the word go, I'm going to just try to hold the mouse to the left, but I'm going to fail here. We see that the number of decoys and targets that are found at each charge state is already showing that we have a larger number of matches to target sequences than we do decoys. And I want you to keep in mind that that represents the fact that the target decoys, the target matches are what it calls non-decoys up here, are a mix of PSMs that are falsely identified and PSMs that are correctly identified. The decoys are all falses. So in effect, this mixture model that it's fitting is trying to determine what the shape of the PSMs for decoys look like, and it knows that those are the falses. It can then try to match the rest of the distribution, those represented by higher scoring target matches, as a way to find where the true distribution is located. You will see that occasionally the software throws odd little errors about unknown file type. Some of these features sort of behave better if you do a search from MZML format instead of RAW, but generally speaking, that's not going to come into play for anything that we are doing. All right, we can see that the accurate mass engine is going to come into play here. We did this search with a pretty wide tolerance of 20 ppm, 20 parts per million. I think most mass spectrometrists would be pretty disappointed if their Orbitraps or their FT instruments were 20 ppm off target. So in effect, by doing a search with a 20 ppm window, we have matches that are coming from all the way across that entire mass error range. The software knows that things that have mass errors closer to 0 tend to be more likely correct than those that are closer to 20 ppm in error. And so the software is able to use that as something that the scoring engine itself isn't contributing, but that it itself can detect as a useful discriminant between correctly identified PSMs and falsely discovered PSMs. All right. I did mention that the database search of MSFragger does not necessarily consume the most time in this pipeline, and here you can see that Peptide Prophet is, in fact, consuming a fair bit. It's also the case that this is another case where your CPU is going to get a pretty fair beating. Here we're using between a third and half of the CPU cores to keep up with working through these complex data structures. So what is the ideal distribution of PSMs and precursor charge? I would note that today, most people running Orbitrap class instruments tell their instruments not to collect tandem mass spectra for singly charged precursors. Further, they say that if I am unable to determine what the charge state for a peptide ion is, that I'm not going to collect the tandem mass spectrum for that either. So in practice, for bottom-up data from this class of instrument at least, we very rarely see a large number of +1 ions collected. All right, so here we see that we're now moving into the protein prophet stage. The software is reading from these PEP XML files that have been created. I know that people have probably seen PEP XMLs before, but I just want to note that the PEP XML format is a format created by the Institute for Systems Biology in Seattle many years ago now. for storing raw PSM data. And the transproteomic pipeline that also came from ISV is able to write its results back into the PEP XML format. So you might say, well, gosh, PEP XML has been superseded. We now have this new and cool MZ IdenTML format. Shouldn't we be writing everything in that? But the truth is, there's a world of software out there that can still make effective use of the PEP XML format. And frankly, you can read a lot of these PEP XML files and write MZ IdenTML files if you really wanted to. So it's not as though there's an apples and oranges and everything old is superseded and shoved aside. There's a world of software out there that still makes use of these old formats, and we haven't just discarded it. All right. So having executed the filter in Philosopher, we are able to begin applying a specified false discovery rate to these data sets to cut down the error rate at the PSM level, or at the peptide level, or at the discoverable ion level. And importantly, we can control it at the protein inference level as well. So we can already get a quick sneak peek that this quick analysis has still been able to identify more than half of the proteins in the E. coli proteome, which is, as I recall, about 4,450, I think. So we can see that these relatively quick experiments of just single shots in 6 replicates were still sensitive enough with modern instrumentation. I believe this was on a Q-Exactive to give us a really deep look into that proteome. Is it big enough is probably the question that should come to mind, though. Do we have a guarantee that just because a protein is one that's detectable by top-down proteomics, that it will also be identified with a relatively quick 1D shot in bottom-up proteomics? And that is an interesting question, because some of the proteins that are detectable by top-down proteomics are not necessarily mass spec friendly at the peptide level. Imagine that you had a protein that was highly hydrophobic throughout its length. The number of lysines and arginines within that protein sequence would be really problematic for trypsin digestion. As a result, it would be very unlikely that you would have peptides identified for it in a tryptic search, because trypsin had nothing to do. There were no cutting sites for it to cut. As a result, something like that would be missed. And while I'm talking, what has the software done but to finish? So we see that the filter was applied, the software was able to complete its output, it's done this synchronization of PSMs and proteins, it's completed its final reports, and now that working directory contains all the reports. Did we see something where it said explicitly that it wrote the FASTA file? No, but let's go ahead and check. Let us now go over to the bottom-up directory. We see that it has gained, I meant to be in the MSFragger directory. We told it not to write its outputs in the bottom-up directory, but rather in the MSFragger directory that we created. So we see that a variety of files fall in here, and to give away the thunder at the start, I just want to point out that the very first of these, when I sort by type, is protein.fas. What that is to say is that the software has now output a sequence database in FASTA format, that's what the FAS comes from, that represents all of the proteins that were confidently identified via this Philosopher analysis on the back end of MSFragger. So we do have our sequence database. We can open up our favorite text editor and now copy our protein.fas over here. And you can see that it's formatted just as you would expect, perhaps with one small change. I would note that when the software outputs the FASTA sequence database, it puts all of the sequence on one long line. So that may be a little difficult to read if you're using something like Notepad, but it is in fact a legitimate FASTA file format. It is possible, of course, to reformat this in a way that limits the lines to be only 80 characters long or 60 or whatever you like. It's probably worth asking, did any of our decoy proteins marked with rev underscore make it in here? And what we note is that none of them did. So if the protein sequence made it into the target protein list that was confidently identified, it is in here. If it doesn't, it's not. What about contaminants? Did we find something like keratin in here? So we can just do a quick search for keratin, and we see, sure enough, that K2C1 human keratin was in there. Now, how did that get into the sequence database? Remember, we started with a sequence database, a reference proteome for E. coli directly downloaded from UniProt. The E. coli database, as downloaded from UniProt, does not contain keratin. But remember, when we added decoy sequences to our database, we also added contaminants, and that's where keratin comes from. It is not marked with a particular signifier to specify that this came from the contaminant set, but in this case, anything marked _human is definitely going to qualify. If you spot any yeast proteins in here, that would be a similar case, because the contaminants proteins are not just human ones. We can do some other operations like ask how many times does a greater than symbol appear in this file to give us a count of how many protein sequences are here. I believe that's feasible, but I'm not going to look it up at the moment. All right, but here we see that just in the course of this video, we've been able to do all of this data processing, starting from 6 raw files and a sequence database downloaded from UniProt to a subset database that we can now use on our top-down proteome. But as I was saying, we should be really careful about assuming that any protein detectable by bottom-up, that only proteins detectable by bottom-up can be seen by top-down. Top-down surely can identify some proteins that would not cut the mustard in a triptych bottom-up analysis. All right, thank you very much for watching.